Hello everyone, welcome back to Math with Allison. Today we're continuing our series in sequences and series, and we're going to be talking about the convergence of a power series. So let's go ahead and dive into it. We're going to begin with a power series, of course. So we have the summation from k equals 0 to infinity of our c sub k. So these c sub k's are going to be our coefficients. They're going to be a function of k, but they're going to be the coefficients, right? And then we have x minus a all to the power of k. And this little a right here is going to be the center of the power series. So let's go ahead and see an example of this. Here we have the summation from k equals 1 to infinity. So notice we can start at a different spot, right? We can start at 1, we can start at 2, we can start at any number. And we have x minus 2 to the power of k. So here we can see the center of our power series is going to be 2. And then we have that divided by the square root of k. And that's going to be like our coefficient. So our c sub k is going to be 1 over the square root of k. And like I said, they're going to be a function of k. Not all the time, but sometimes. So let's go ahead and talk about this. Question, can we find the values of x for which this series converges? Because I'm interested to know when does it converge and when does it diverge, right? And x is going to change that. So let's just go ahead and try and plugging in some random values. We can go ahead and try plugging in, for example, x is equal to 3. If we were to plug in x is equal to 3, we have the summation from k equals 1 to infinity of 3 minus 2 to the power of k divided by the square root of k. If we were to simplify this, right, we know that 3 minus 2 is equal to 1. So we get 1 to the power of k divided by the square root of k. But 1 to the power of k is always equal to 1. No matter what power you raise it to, it's always going to be 1. So this is equal to 1 over the square root of k. So we can identify what kind of series this is. If we rewrite it, we have k equals 1 to infinity of 1 over k to the 1/2. This is a p series, so we can apply the p series test. In this case, our p value is equal to 1/2, right? That's our exponent. And since this is less than 1, we know that this will diverge. So if we were to plug in x is equal to 3, we can see our series is going to diverge. Let's go ahead and try plugging in another value. So let's go a bit smaller, right? Let's plug in when x is equal to 2. Then we have the summation k equals 1 to infinity of 2 minus 2 to the power of k divided by the square root of k. This might have been an obvious one to plug in because we have x minus 2 in the numerator, right? So we know that 2 minus 2 is equal to 0. So we have the summation k equals 1 to infinity of 0 to the power of k divided by the square root of k. And this is equal to the summation k equals 1 to infinity of 0. So you're forever just adding 0. This is going to end up equaling just 0, right? So we know this is going to converge. Now I just chose two specific values of x, but I want to know all the values of x for which this series is going to converge. So is there a way I can solve for all of the values? Because if you have to plug and chug, that might take you a while. And the answer is yes, we can. What we're going to go ahead and use is the ratio test. This is going to help us find all of those x values. So reminder of what the ratio test, we have r is equal to the limit as k approaches infinity of the absolute value of a to the k plus 1 divided by a to the k. So let's go ahead and plug this in. We have the limit as k approaches infinity of, first I'm going to write a to the k plus 1. So we get x minus 2 to the k plus 1 divided by the square root of k plus 1. And instead of dividing, I'm just going to go ahead and multiply. So multiply by the reciprocal of, that's going to be the square root of k, divided by x minus 2 to the k. So let's go ahead and simplify this. We get the limit as k approaches infinity of, and here we get x minus 2 to the power of k times x minus 2, right? I just went ahead and split that up, divided by the square root of k plus 1. This is going to be times the square root of k over x minus 2 to the power of k. So here we can see what cancels out, right? X minus 2 to the k, that's going to go ahead and cancel out. So let's go ahead and rewrite this. First, in the numerator, notice I have this right here. We have x minus 2. That does not depend on k at all, so I can take it out to the limit of the limit, right? So let's go ahead and take it out. We have the absolute value of x minus 2. It has to stay in the absolute value, right? And now we have the limit as k approaches infinity of, this is going to be the square root of k over the square root of k plus 1. Since both of these are in the square root, we could actually just go ahead and combine it, right? This is going to be the square root of k over k plus 1. Now let's think about this. We're taking the limit as k approaches infinity. So when k gets really, really large, k plus 1 is going to be super duper close to k. So this is like approximately equal to the limit as k approaches infinity of the square root of k divided by k. But the square root of k divided by k, that's just equal to the square root of 1, which is just equal to 1. So what's the limit of 1 as k approaches infinity? It's just equal to 1. So we get x minus 2 times 1, which we can just write that as the absolute value of x minus 2. Now let's go ahead and think about this in terms of the ratio test. I know that the series will converge absolutely when our radius is less than 1. So we found that r in this case is equal to the absolute value of x minus 2, and we want this to be less than 1. Now this is going to help us solve for the x values. So initially when we use the ratio test, it helps us write it as a function of x because we're taking the limit of k. So those values are going to converge or going to diverge somehow, and we're left with a function of x. Now we're going to go ahead and take advantage of the fact that we have a function of x, and we want to find all the x values for which this is less than 1. So this is going to give me two cases, right? We have x minus 2 is less than 1, or we have negative x minus 2 is less than 1. So here, if I solve for x, I just add that 2 over. I get x is going to be less than 3. Now, if I multiply that negative 1 over, I have to switch the signs of the inequality. So we have x minus 2 is greater than negative 1. Adding 2 from both sides, I get x is greater than 1. So what does this tell us? It tells us that the series converges absolutely when x is between 1 and 3. But this isn't quite our final solution yet because we have to test the endpoints. Can it equal 1? Can it equal 3? Well, if we look back at when we first plugged in values, we actually plugged in when x was equal to 3. And we found when x is equal to 3, this is a p series and that it will diverge. So we know when x is equal to 3, our series will diverge. Okay, so now all we have to do is plug in when x is equal to 1. So here we get the summation, k equals 1 to infinity of, that's going to be 1 minus 2 to the power of k over the square root of k, which we can go ahead and simplify this. So we get the summation k equals 1 to infinity. That's going to be negative 1 to the power of k divided by the square root of k. Now notice what kind of series we have. We have an alternating series, right? Because of that negative 1 to the k. So let's go ahead and apply the alternating series test. Here we have our a sub k is equal to 1 over the square root of k for our alternating series. The first thing we want to check is that if this little sequence is going to be non-increasing, so it gets smaller and smaller each time. In our case, 1 over the square root of k is going to get smaller and smaller for every value you plug in, so we know it's non-increasing. We also want to check the limit as k approaches infinity of our a sub k. So if I plug that in, we get 1 over the square root of k, and we want this to equal 0. And we can actually see, right, as we plug in larger and larger values, this is going to converge to 0. So because this is non-increasing and the limit goes to 0, we know that this is going to converge. So what does that tell us about our series? We know this series is going to converge absolutely when x is bounded between 1 and 3, and x can also equal 1. So what other pieces of information do we know about this series? We know the interval of convergence is going to be between 1 and 3, right? We are going to include 1, we're not going to include 3. We also know the radius of convergence. That's just going to be from the center of the radius. So here we go from 1 to 3. So obviously our center is going to be 2. This is going to be the real number line. So we're going from the center all the way out to our endpoints. We're finding that distance. So for us, that distance is going to be 1. So let's go ahead and see a summary of all that information we just talked about. We can find the interval of convergence and the radius of convergence of a power series by using the ratio test. So we're going to take the limit as k approaches infinity of a sub k plus 1 divided by a sub k, and we want that to be less than 1. So we're going to find all of the x values that make this true. Do not forget you also need to check your endpoints because they could still converge at one of the endpoints or maybe both of the endpoints. So now that we've seen an introductory example, let's go ahead and actually work through a real example. So here we have the series k equals 0 to infinity of x to the power of k divided by k factorial. So the first thing we want to do is apply the ratio test. So we're going to take the limit as k approaches infinity of x to the k plus 1 divided by k plus 1 factorial times, and we're going to divide by a sub k, so I'm just going to multiply by the reciprocal, k factorial divided by x to the power of k. So let's go ahead and simplify this. We get the limit as k approaches infinity. This is going to be x to the k times x divided by, now what I'm going to do is I'm going to pull out that k plus 1, and I'm left with k factorial times k factorial over x to the k. So I simplified it so I could see what cancels out. So we get x to the k cancels out, and we also get k factorial cancels out. So we have the limit as k approaches infinity of x in the numerator and k plus 1 in the denominator. Now, x is not a function of k, so I can take it out of the limit. So we have the absolute value of x times the limit as k approaches infinity of 1 over k plus 1. Now, what does this limit approach? As k gets larger and larger, this is going to get closer and closer to 0. So this is going to be equal to the absolute value of x times 0, which is just equal to 0. Now, what does this tell us? We want to find all the values where we take the ratio test and we find that it's less than 1. In our case, 0 is always less than 1, no matter what value of x you get. So this tells us that this series converges absolutely for all values of x. So if you want to write it out as an interval, right, we're going from negative infinity all the way to infinity. And also our radius of convergence is also going to be infinity, right, because we have an infinite interval. So if you end up with a value, right, if you end up with 0, if you end up with a number, if it's less than 1, that tells you it's going to converge for all values of x. Doesn't matter what values of x you're going to plug in, you're going to go ahead and converge. So let's go ahead and try another example. Here we have the summation k equals 0 to infinity, negative 1 to the power of k times x minus 2 to the power of k divided by 4 to the power of k. So let's go ahead and apply our ratio test. We get the limit as k approaches infinity of negative 1 to the k plus 1 times x minus 2 to the k plus 1, and this is going to be divided by 4 to the k plus 1. And now I'm just going to multiply by the reciprocal, right? So 4 to the k divided by negative 1 to the k, x minus 2 to the k, absolute values. So let's go ahead and see what cancels out. First of all, we don't need to worry about the negatives because we're taking the absolute value, right? It's always going to be positive. Now we have x minus 2 to the power of k is going to cancel out, and we're just left with x minus 2 in the numerator. And then we get 4 to the power of k is also going to cancel out. So we're just left with 4 in the denominator. So let's go ahead and write that. We get the limit as k approaches infinity of the absolute value. We have x minus 2 in the numerator, and we just have a value of 4 in the denominator. So let's go ahead and think about this. We're taking the limit of k. There are no longer any values of k in our limit. So the limit is just equal to 1. One way you can think about it is we can pull out that x minus 2 divided by 4, and we have the limit as k approaches infinity of 1. The limit of a constant is just equal to that constant. So this is just equal to 1. So now we can find our x values, right? Because we want this to be less than 1. So what we can do first is we can multiply that 4 over. So we get x minus 2 is less than 4. And now we're going to have two cases, right? X minus 2 is less than 4. And we have negative x minus 2 is less than 4. So if I add over 2, I get x is less than 6. And here I'm going to multiply by negative 1. So I have to swap the sign and we get negative 4. And now I'm going to add 2 over. So I get x is greater than negative 2. So right now I have the interval from negative 2 to 6. So here immediately I can tell my radius of convergence, and I'm just going to go ahead and call it r, is going to be equal to 4. My radius of convergence is 4, but I also need to check my endpoints because what if it converges at one of these endpoints? So first, let's go ahead and plug in x is equal to -2. We have the summation k equals 0 to infinity of, and I'll scroll up for us, we have -1 to the power of k, and that's going to be, -2 minus 2 to the power of 4 divided by 4 to the power of k. So let's go ahead and simplify this. We get the summation k equals 0 to infinity. And here we have -1 to the k, and that's going to be -4 to the k divided by 4 to the power of k. So here, -4 to the power of k, I can split that into -1 to the power of k, and then that's going to be 4 to the power of k. So here we can see what cancels, right? These two cancel each other out because -1 times -1 is always going to be +1. +1 times +1 is always going to be +1. And then here the 4 to the k also both cancel each other out. So we're left with the summation of k equals 0 to infinity of 1. Now, really what this is doing is it's adding up 1 an infinite number of times. And so this is going to go ahead and diverge to infinity. So when x is equal to -2, this diverges. So we cannot include this endpoint. Let's go ahead and see what happens when we have -6 or +6. So we have x is equal to 6. We have the summation k equals 0 to infinity, -1 to the power of k, 6 minus 2 to the power of k, divided by 4 to the k. Okay, so let's notice what cancels out. We get that 4 to the k both cancel out. So we're left with the summation of k equals 0 to infinity of -1 to the power of k. Now, this is going to alternate, right? This is going to alternate between -1 and +1. So if you think about it, if we plug in 0, we get -1 to the 0 is equal to 1, and then we get -1 plus 1. Oops, -1 plus 1 minus 1 plus 1, so on and so forth. Why is this alternating? Well, first we get 1, and then we subtract 1 and we end up with 0. But then we add 1 again, so we get 1. But we subtract 1 again, so we get 0. So this is forever alternating between 0 and 1. And since it's forever alternating between those two values, it's going to go ahead and diverge. So this is going to diverge at both endpoints, which means our interval of convergence is just going to be from -2 to +6, and our radius of convergence is going to be equal to 4. And that's our solution for the second problem. Let's go ahead and try one more. Here we have the summation k equals 1 to infinity of k factorial times x to the power of k. Just looking at this, you might have a guess on what's going to happen here because we're not dividing by anything, so there's no way anything's getting smaller. We're just multiplying by k factorial, which is going to be quite large. But let's go ahead and see what actually happens. So we take the limit as k approaches infinity. Here I have the absolute value. So I have, oh, actually we can just write this as a fraction. So k plus 1 factorial, x to the k plus 1, divided by k factorial x to the k. So if you wanted to rewrite this, you could. We can see it all worked out here. We get, if I pull out the k plus 1 from the factorial, I get k plus 1 times k factorial, and that's going to be x to the k times x divided by k factorial x to the k. Alrighty, so our k factorials cancel, and our x to the power of k also cancels. So here we have the limit as k approaches infinity of, and that's going to be k plus 1 times x. So remember, our x is not a function of k at all, so we can go ahead and pull that out. So we have the absolute value of x times the limit as k approaches infinity of just k plus 1. Now, what happens to k plus 1 as k goes to infinity? It goes to infinity. So we get the absolute value of x times infinity, which is equal to infinity. And remember, we want to find all the values for which this is less than 1. Infinity is not less than 1. So we're not going to find very many x values for which it converges. And the reason I say very many is because there is exactly one solution. And it's going to be when x is equal to 0. So when you find that it's equal to infinity, we have to be careful for that specific 0 value. Because if I were to plug in x is equal to 0, right, we get the summation k equals 1 to infinity of k factorial times 0 to the power of k. This is just equal to the summation, right, of 0, which when we add 0 up forever, it's just equal to 0. That value, whatever value it is always going to be included in our interval. So if we go back up to here, we have the x value for that makes this 0 is going to be x is equal to 2. And so 2 is going to be included within our interval. If we go to our first example as well, right, we have x to the power of k, so that's going to be when x is equal to 0. We always have to include that specific value, and it's going to be the center of our power series, right? So for us, this is going to go ahead and converge only when x is equal to 0, right? So here, if you want to talk about the interval of convergence, it's not going to be very interesting. So interval of convergence, this is literally just a point. It's when x is equal to 0. So then the radius of convergence is also going to be equal to 0. So that is our final solution right there. So that's all I have for us today in this video. If you enjoyed it, I have many more like it, so make sure to check them out. Otherwise, please leave a like and a comment if you have any questions. Thanks for watching.